Hello, everyone. Thanks for coming to my talk. Today, I'm going to talk to you about legacy phosphorus in Lake Okeechobee. Before getting started, I want to thank my co-authors for help with data collection and overall discussion, all things Okeechobee and phosphorus. I want to thank the South Florida Water Management District for funding the data collection effort associated with this project, the most recent aspect of this project, actually. Before getting started, I want to acknowledge the lands in which this research was conducted. Today, I'm presenting from the traditional lands of the Calusa, and Lake Okeechobee is within the Greater Everglades ecosystem. And so the Everglades, as we know it today, is rich in history of both modern and traditional First Nations. From the lands of the Calusa, Taino, Tequesta, Miami, Gokata, Jaga, Miccosukee, and Seminole, these lands are the Everglades, and they're steeped in this indigenous history. We pay respect to their elders, past and present, and extend that respect to their descendants, to future generations, and to all indigenous people. We recognize the ongoing relationship of care that these indigenous nations maintain with the land, and we extend our gratitude as we live and work as humble and respectful guests upon their territory. We acknowledge and thank the Miccosukee tribe of Indians of Florida and the Seminole tribe of Florida for being stewards of this traditional territory and history. So Lake Okeechobee, in several tribes have the name Okeechobee, or the word. In several translations, it's considered called Big Water. So back in the historic days, pre-drainage, pre-human impact, during the wet season, the Kissimmee chain of lakes and Lake Okeechobee would fill up with rainwater, overflow its banks, and flow down, southerly down the peninsula and into the historic Everglades. This flow pattern, this hydrology, has driven a lot of this vegetation distributions within the system. And so from the southern rim of Lake Okeechobee, we have swamp forests historically, sawgrass plains, all the way down into the southern marl-forming marshes. Now, since drainage has happened, since flood control has occurred, there's been damming, diking, canals being dug, and levees being built, effectively compartmentalizing the system and altering the hydrology. You can see on this figure here to the right, it has some of those water control features in there, canals and levees, but and underneath that is the vegetation, then some of the remaining historic vegetation distribution, albeit vastly reduced. So in the past 40 odd some years, Lake Okeechobee has gone under an evolution of sorts of water management. And here's up on this figure here, you can see a couple different acronyms under this management band here. And each operations plan operated the lake in a different way. Some not so favorable for ecology, and others still not favorable, but better than the last. During this period, also regulatory programs were developed, and restoration efforts also to restore the Everglades water hydrology, essentially, as well as the water quality. In this 40 some odd year period, we also have seen extreme climatic events during this period through tropical activities, as well as La Nina, El Nino, and droughts. Here's a quick figure of the 40 some odd year period on the top panel here is inflow and outflow to the lake, discharges. The middle panels here are load, total phosphorus on the left and total nitrogen to the right. And on the bottom is the flow weighted mean concentration for any given year. And you can see that the system is, from a discharge perspective and a load perspective, is extremely variable. Variable is going to be this buzzword in this talk. You can see that some years we are in flood conditions, I guess you can call it, with really high inflows. And then there's some years where we have very little inflows and outflows from the lake. Along with those discharges, we also have loads, phosphorus loads in the order of 10 to the 4 kilograms per year, and nitrogen times 10 to the 6 kilograms per year. one thing that's interesting is if you look at it from a trends perspective in this long time series, we've seen actually declines both in inflow and outflow total nitrogen concentrations from the lake. But outflow phosphorus loads have actually significantly increased over this 41 period, from 1979 to current, and more dramatically, I guess you can call it, in the more recent history. Now, if we look at this from a within the lake perspective, so this outline here is Lake Okeechobee. I'm going to orient you guys to these plots. So on the left are the trend plots over 1997 to 2020 time period, and on the right is the average geometric mean concentration across that across the lake and across time. And so on the plots, we have this interpolation, it looks like you can call it, and this is the Thiel-Shen slope for each one of these sites. And then the color of the points here, and I apologize if you're colorblind, but the green means increase, significantly or not significant. Meanwhile, the red points are significant. So it's a p-value less than 0.05. And so this top group here is nitrogen, the middle is phosphorus, and the bottom is chlorophyll. And you can see from the trends perspective, we're for the most part, and it joins up with that outflow and inflow nitrogen concentrations, is we're increasing direction across the lake from a perspective, with several sites significantly decreasing and others not. And you can see that, you know, across the lake, there's a little bit of a gradient here from north to south. Well, north east to south. In the middle here is phosphorus. Not many sites are significant, you know, trend direction, but there is a pretty abundant or a pretty wide spread of magnitude changes across the lake. So we have in the southern portion of the lake, concentration is significantly increasing, and then up in the north part, significant increase or decreasing. And then you can also see on the annual geometric mean concentrations, the average concentrations, you can see that the lake is not homogeneous by any means of phosphorus. And you can see along the edge here, the phosphorus concentrations are actually lower, and that coincides with the littoral zone of the lake. And then in the middle here is so some people call pelagic or limnetic zone of the lake, where it's essentially open water. And chlorophyll is kind of a mixed bag trends wise, as well as concentrations wise. So here's actually 3 maps of spatially intense sampling of sediments of phosphorus across the lake in 88, 98, and 2006. And this is kind of a traditional kriging method. And you can see, just like that water quality I presented before, along the edge, you have lower phosphorus concentrations. The yellow and light green is lower. Meanwhile, blue is higher. And that blue area tends to be right in the middle. Now, fortunately, because of COVID, 2020, 2019, 2020, and into 2021 was the data collection effort. And the data has been collected. It's just sitting in the lab, finalizing, getting the phosphorus analyzed finally. I think the data is pretty much done, and we're just waiting on QA/QC. So I wanted to kind of get it for this talk, but unfortunately we didn't. So we can look at it from a ordinary kriging approach, but we can also look at it from a general additive model approach, kind of showing or seeing the effects of year, since we have these years, and then spatially as well. Unfortunately, that 2020 data point would be really nice to include in this, but generally you can see that from a year's perspective, we're actually declining in phosphorus concentrations. This effect is showing a decline in the effect of year. And then in across space, I guess you can call it, we have that same trend where the outer edge of the lake has a smaller effect, a negative effect on the spatial distribution, and then that limnetic area has a positive effect on the spatial distribution of the data. Now, looking at from it, we have water column, water quality coming in, we have sediment nutrient concentrations, we can also look at it from an internal loading perspective. And so if we look at just the net P sedimentation coefficient across this period of record from 79 to 2020, this 40 some odd year period, we can see that at times, most of the time, almost about 47% of the time, if you look at it from a year perspective, we're at that coefficient is actually less than 0, signifying that the sediment is a source of phosphorus to the water column. We can take another look at this. So get it, from the water quality perspective, averaging it across the lake, you can see these red dots and lines here is the average, spatially average concentration across the lake, and it's ticking up, it's increasing quite dramatically. And then we can look at it from a simple model perspective. So this volume meter model takes into account load coming in and just purely sedimentation, doesn't take into effect necessarily biology per se. And you can see that based on that simple model, hypothetically, concentrations should just be motoring on along kind of relatively steady. Now that difference between this meter model and the spatially average observed data, you can see that starting to kind of diverge from itself, indicating that we could, that loading is a significant contribution to that. And so phosphorus, and to some extent nitrogen, I didn't get to jump into that too much, inputs into this lake are highly variable and driven by kind of upstream inputs. So with those significantly increasing phosphorus outflow trends, potentially impacting or could potentially impact downstream systems. Now within the lake, trends in phosphorus, nitrogen, and chlorophyll are extremely variable, driven by ecosystem factors. So you have that littoral wetland area versus the limnetic area that are really affecting transfer of nutrients. And then spatially and temporally across the lake, the sediments mirror that water column, or maybe the water column mirrors the sediments. I guess it depends on your perspective, but we have this mirroring throughout the system. And so the difference from the input to output and the water column to sediment concentrations is largely to do high internal loading, so that if the sediments didn't have that huge store of phosphorus in it, the water column wouldn't necessarily, hypothetically, be ticking up as fast as it is. So I want to thank everyone for coming to my talk. I know I breezed through a bunch of data, but if we have chances for questions, that's great. If not, feel free to email me or hit me up on Twitter. Thank you very much.